Alrighty then, what I want to do is talk about Quambers. Now this is, I'm going to be reading from just a little document I have here. It's actually complete, and I'll be partially reading from it and partially just creating it. And so, uh, everybody knows that you can't add Quambers to vectors. Excuse me, let's take that again. Uh, Everybody knows you can't add scalars, that is real numbers. For this discussion, scalars and real numbers are the same thing. So everybody knows you can't add scalars to vectors. But what if you could? So let's start the discussion with an inner product vector space with real coefficients. That is, real scalars. Okay, that's what I was just saying before, said a little different. So the scalar field for the inner product vector space is the reals. Suppose that you could add scalars and vectors, and suppose further that you wanted to make a number system out of the results. In other words, if you had an object whose a two-component object, and the components of the object, the Quamber is what I'm calling it, would be accessible via a reflection operator over the vector space. In other words, it would be an operator that negates the vector component of the Quamber, but leaves the scalar component unchanged. So if you have that kind of operator, you can, given any Quamber, you can easily construct just the scalar component, and you can also easily construct the vector component only of that Quamber. Now, if you do this, if you're making a number system out of this, how many of the usual rules of algebra can still hold? So what I did, what you can do, is you start listing potential axioms, and you can go ahead and assume that almost all, will hold, and but there's going to be at least one thing that has to change, and so if there were such a thing, what would it be? How much? In other words, how much of business as usual, that is, uh, uh, vector algebra as usual, how much of it can remain intact, and how much of it has to change? Now, so given that we're defining a Quamber as the sum of a scalar and a vector, then, and given that every Quamber has a scalar component and a vector component, and that the Quamber is the sum of its two components, the scalar component and the vector component, right? So now component-wise addition of Quambers gives the numerical sum, and it's commutative. So as far as addition is concerned, everything goes over intact, which leaves the interesting question of the numerical vector product of two Quambers. In other words, do all the rules go on as before? Well, let's go find out. So the product of two Quambers would be the product of their respective two-component sums. And that would distribute out to be a four-component sum. Now, so one of the things that we're going to keep here, looks like we can get away with it, is the distributive law. It's the same as always. Okay, now, so what you do is you group the two vector terms of this four-component sum together to form the vector component of the product, and then you group the remaining two terms together to form the scalar component of the product. One of these scalar products scalar terms is going to be the numerical product of the scalar components of the original Quambers. The other scalar component is the numerical product of the vector components. So let me just do a little bit of verbal algebra here. If Quamber A is the sum of scalar A plus vector A, and that's always the case, and if Quamber B is the sum, the numerical sum, of scalar A plus, scalar B plus vector B, then the product of Quamber A and Quamber B, when distributed out, is just going to be the sum, well, it's going to be the product of the sum of scalar A with vector A and times the sum of scalar B and vector B. In other words, it's the product of two factors, each of which is a two-component sum. It gives you four terms, and those four terms are going to be scalar A times scalar B plus vector A times vector B plus scalar A times vector B plus scalar B times vector A. Well, obviously the product of as usual, the product of a scalar and a vector is a vector. So the two vector terms add together to give the vector component of the product. In other words, the vector component of the product is going to be scalar A times vector B plus scalar B times vector A. The remaining two terms are going to be scalar A times scalar B plus the numerical product of vector A times vector B. And everything is cool except there's something that's undefined, which is the numerical product of two vectors, or two vector components. Same thing. Okay, so now, if you remember, we started with an inner product vector space, and the inner product of two vectors is a scalar. Now, the scalar product of two scalars is a scalar. So in other words, scalar A times scalar B is a scalar. And we are going to need to have vector A times vector B to be a scalar as well. But then that kind of makes sense because we could just have the scalar product we can have the numerical product of vector A and vector B be related to the scalar, the scalar product, is the dot product of vector A with vector B. Well, here we get a little bit creative, just minutely, and this is the key to the universe practically. And what we do is we say that the numerical product of two vectors you're going to define to be the negative of their dot product, your scalar product, which means that for the scalar component of the product of those two quambers that we started with, it's going to be scalar A times scalar B minus vector A dot vector B. And from this point on, everything is, we're launched. We're on the boat. This discussion will never stop from this point. It just gets deeper and richer and deeper and richer and grander. Okay, so now, the question then arises as to what you can keep and what you must throw away. And it turns out that everything goes through, with a single exception. And that single exception is the, it's in multiplication. So addition is the same as always. And for multiplication, it turns out that if you just compute um, the four terms and regroup them of the product of two Quambers, then it'll turn out to be commutative. It's just very simple. It's slam dunk identity. Okay, so then that leaves the question of is it's distributed. So is oh, by the way, yeah, if you go check out um, the equality of a distribution, it turns out that that's an identity as well, so you haven't lost anything there. And what that then leaves us is the question of associativity. And darn it, associativity does not hold for numerical products of Quambers. So in other words, the numerical product of Quamber A with the numerical product of Quamber B and C is different from the numerical product of Quamber A and B with Quamber C. So what we could do is, since they're different, we could sort of measure how much, or to what degree, or in what manner, those two different associations of a triple Quamber product turns out to be. And so we just take one of those associations, multiply it out into components, piece cake. Then we go and we take the other association and multiply that out, and then we subtract the two. We'll get the negative depending upon how we define the associator. In other words, which of those two associations are we putting subtracting for the other? And we then find that there is a little miracle that happens, kind of makes the whole thing worthwhile. Because I mean, it was looking pretty grim there for a while. I mean, for about the first 2 or 3 days, I just had this sick feeling in the bottom of my stomach about like, oh no, we're not really losing associativity, are we? And we sure did. But what we gained is that it turns out that the associator, that is the difference between those two associations of a triple Quamber product, that is a pure vector. Its scalar component is 0. 0 scalar. So, and then all of a sudden, sort of like the clouds part and the sun shines through and we're in heaven. And we're right on the verge of certain identities that lead up to Heisenberg's uncertainty principle, and which calls into question the interpretation that the uncertainty principle is really a physical principle, and when it might, and it actually appears to be, the case that this is all just an algebraic identity with Quambers. Now, I'm going to stop this for now. I've been talking way too long, and allow you to go and maybe look up some of what I've said on the web, or maybe just take this little discussion here and go through it and do the whole dang thing yourself and see what you get out of it. But before I do that, just one thing, and that is I use the star notation. Here's the notation that I use, a little side about notation, and that is a Quamber A. I have a way of writing a Quamber, and what I'll do is I'll use the same symbol. It might be a single letter, or it might be a word, that is a string of letters, but I'll use a single symbol for both the Quamber, its scalar component, and its vector component. But I have a special way of writing Quambers0.avi, and I have a distinct but special way for writing scalar A, that is the scalar component of that Quamber. And the way I do it is for the vector component of that Quambers0.avi, I just take the symbol A and put a little arrow over it, and I'm off and running. So we get the identity that Quambers0.avi is equal to the sum of scalar A plus vector A. Now, there's another operator, which is the reflection operator, also known as the conjugate. And what it does, well, I'll just do this algebraically, and then I'll tell you what it means geometrically. The conjugate of Quambers0.avi is the conjugate of the sum of the scalar and vector components of A. And we're going to allow this operator to distribute over the plus sign there. So that would equal the conjugate of the scalar part plus the conjugate of the vector part of Quambers0.avi. And I'm going to define the conjugate of the scalar part to be just the scalar part. So in other words, scalar A conjugate is just scalar A. And I'm defining the conjugate of the vector component of A to be just the negative of the vector component. So that the conjugate of Quambers0.avi is the conjugate of scalar A plus the conjugate of scalar B, which is the same as scalar A minus vector A. That's what I mean by reflection. In other words, the conjugate operator, the reflection operator, simply negates, given a Quamber, the conjugate negates the vector component only and leaves the scalar component unchanged. This allows us to introduce a norm onto this Quamber space. And the norm on the Quamber space is simply the product of the Quamber with its conjugate. Let's think of another way to do this. We might want to say divide that by 4, but I think right now I'm going to keep talking as though that's not a good idea. I don't think I've ever really paid much attention to doing it that way. Might be a good idea though, you know. I'm defining the norm to be, man, that other alternative is looking really attractive. I'm so glad I'm actually getting this recorded, just talking about it out loud. I've been at this for 12 years, and it hasn't quite occurred to me to define the norm to be 1/4 of the norm that I'm used to using. So, in the norm that I'm used to using, and I will continue the discussion with, is the norm of Quambers0.avi is the product, the numerical product of Quambers0.avi with its reflection. That is, it's also the product of Quambers0.avi times conjugate of A. Now, oh, by the way, just in case anybody doesn't know how I would write the conjugate of the Quambers0.avi, I would write it as a superscript to the right of the letter for the Quamber. And one other point to make is the way I do things is I use a hollow font for the Quamber. I use a very simple text font for the scalar component of the Quamber, and I then notate the vector component of the Quamber as using the same font as I do the scalar, as I use for the scalar. However, I put a vector over it. An alternative, and I think slightly more confusing in practice, way to do things would be to have a symbol for the scalar component like a prime or something like that. Um, uh, but and then to have use the asterisk for sort of the right asterisk, the right exponentiated asterisk as the operator for your vector conjugation, and or well for the for the vector component. Did I mean this? Okay, I kind of got lost. Um, I kind of got lost on what I was saying. So, with the whole thing, I would just have hollow font A is equal to plain font A plus plain font A with a vector struck over it. So that's what I meant to be saying. Um, and if you do things that way, then it makes it much easier to keep track of, to keep, makes it notationally much easier to keep track of the scalars and the vectors. Because the scalars don't got no vector over on top of them, and the vectors do have a vector arrow on top of them. So, and one of the, see, I intend to have this notation be absolutely, completely transparent, at least to the extent possible, you know. To paraphrase Einstein, as transparent as possible, but no more transparent. Okay, now, um, oh, and here's the way to define, well, those of you who already know how this is, how we're going to define the scalar component of Quamber and how we're going to define its vector component. If you know that, or if you don't want to hear the answer, you can hum for about 30 seconds while I say how to do it. And maybe run from the room and then come back quickly. Okay, so now, scalar component of Quambr is the sum of the Quambr, well, it's half the sum of the Quambr with its conjugate. And the vector component is half, that is, the vector component of Quambr is half of the difference between its scalar component and its vector component. That is, it's scalar A minus vector A. And that's the, oh, excuse me. I'm going to do this again. Okay, run out of the room again. I'm taking it from the scratch. Okay, so just to make sure I get it right. The scalar component of Quambr A is half the sum of Quambr A with its plus its conjugate. The vector component of Quambr A is half the difference between Quambr A minus Quambr A conjugate. I think I got it wrong the first time. The second time I just said that is correct. So enough. Go you forth and check all this out. Have fun with it. And we're just kind of like climbing up the tip of the iceberg onto the mountain. There'll be way more to go.